Hi guys, welcome to our video lesson in which we are going to be factoring polynomials in quadratic form. So sometimes an expression of the form AU squared plus BU plus C, where U is an algebraic expression, is said to be in quadratic form. The factoring techniques you have studied for quadratics can sometimes be useful to factor such expressions. Now, obviously, this looks like a quadratic to us, but what we need to understand is that this does not say AX squared plus BX plus C. The purpose of using the U is to take the place of maybe a term that has a higher degree or something to make it look like a quadratic so that we can use those factoring techniques. So if we look at our first example, letter A, we have x to the fourth minus 5x squared minus 14. Now, we ask ourselves, is there something that we have in common in the first two terms that we could write as that thing squared and then just that thing? And in this case, this x squared right here, could I rewrite x to the fourth as some power of x squared? Could I do that? And the answer to that is yes, because isn't x squared times x squared, isn't that x to the fourth? And if I'm multiplying something by itself, isn't that just squaring it? So yes, so what we have here is we know that if we square x squared, we get x to the fourth. So I could rewrite this original as, in parentheses, x squared squared minus 5 times x squared minus 14. So now you'll probably see that I have something that's the same in my first two terms. So in the place of that is where I'm going to put a u. So when I do that, my new expression looks like this: u squared minus 5u minus 14. And now this just looks like a normal quadratic trinomial that we know how to factor very easily. And we ask ourselves, what multiplies to negative 14 and adds to negative 5? Well, that would be a negative 7 and a positive 2. So factoring this would be u minus 7 times u plus 2. However, we know our original polynomial wasn't with u, it was with x squared. So we put u in place of x squared. So now we need to put that back. So instead of where the u's are, I'm going to put x squareds. So my answer is going to be x squared minus 7 times x squared plus 2. And that is the answer to A. Whoa. Okay, letter B. 3p to the 8th plus 15p to the 5th plus 18p squared. Okay, this one I think has a GCF, so we first need to take that out. So 3, 15, and 18 are all divisible by 3. So go ahead and take out a 3. And then I can also, from all my p's, take out a p squared. So divide all these coefficients by 3 and reduce all my my exponents on p by 2. So I'm actually going to end up with just p to the 6th. Ooh, p to the 6th plus 5p cubed plus 6, because I took out the p squared. Okay, now obviously I have p to the 6th and I have p cubed. Just like when I squared, like over here, when I squared x squared, I got x to the 4th. The same thing is true about squaring x cubed. I would get x to the 6th. So I can rewrite these two terms using a u. Substitution. So first, let me show you. This would be p cubed squared plus 5 times p cubed, and then plus 6. So my common thing that I'm going to be replacing is the p cubed, and I'm going to replace that with a u. So first, keep this 3p squared out front. That's always there. But now I'm going to have u squared plus 5u plus 6. And I'm going to factor that. What multiplies to 6 and adds to 5? Well, that's 2 and 3, so that's u plus 2 times u plus 3. And I'm going to write my final answer, making sure to put my p cubes back in for the u, and I have my 3p squared in front. So 3p squared times p cubed plus 2 times p cubed plus 3. And that is that one. Okay, moving on. Letter C, I have 16x to the 4th minus 81. Well, this only has two terms, and one thing I noticed about the coefficients on these two terms is that they're both perfect squares. So I'm thinking that this is a difference of squares. So is there a way I could rewrite x to the 4th as something squared? Oh yeah, we figured that out right here. X to the 4th is x squared. So this could be written as 16 x squared squared and minus 81. So you might not have to use the u substitution here, but you certainly can. So you can do 16u squared minus 81. So using the u and knowing the square root of 16 is 4 and the square root of 89 is 1. I'm sorry, 81 is 9. You will have 4u plus 9 times 4u minus 9. And then let's put back in our x squared, since it wasn't really a u in my original. So 4x squared plus 9, and then 4x squared minus 9. Just when you think you're done with this problem, look at our second one. 4 and 9 are both perfect squares too. So that's actually a difference of squares. So we can keep going. So we still have the 4x squared plus 9, but then the square root of 4x is 2x. So 2x plus the square root of 9, which is 3, and 2x minus the square root of 9, 3. Okay, last one. 5w to the 6th minus 25w to the 4th plus 30w squared. Okay, what can I take out of each of those? I can definitely take a 5 out, and I could take w squared out. So that will leave us with w to the 4th minus 5w plus 6. 5w squared, excuse me. I only took 2 out. All right, now this is a lot like letter A, where I could rewrite these w's as powers of w squared. Right? So in place of my w squared, I'll put my u. And so I have 5w squared, and I'm going to have u squared minus 5u plus 6. We do our normal factoring. What multiplies to 6 adds to negative 5. Oh, that's a negative 2 and a negative 3. So u minus 2 times u minus 3. Okay, let's put our w squared back in for our u's, and that will be our final answer. So 5w squared times w squared minus 2 times w squared minus 3. All right, so moral of the story, sometimes we can rewrite higher degree polynomials as quadratics, and it helps us factor them. All right, guys, see you in class.